Hello, and welcome to the module Circuit Elements and Schematics. In this module, we'll be going over some of the basic elements that we use in schematics, how do we represent them to avoid ambiguity, as well as some best practices to use when drawing circuits or schematics. We'll also go over some material relating to building circuits, including how to read component values, how to deal with component tolerances, and how to use data sheets to look up information on parts we've never used before. When drawing schematics, there's a couple common elements that we use. Many of these you might recognize from previous classes, so we'll just touch on some of the important features. When representing a battery, you can either use one cell or two, and just make sure that matches what you're actually going to have. The two common types of symbols for a resistor are this one you've probably seen before, as well as sometimes just this box seen here. You can use either one, just make sure you're consistent. To represent variable resistors, we simply add a diagonal line across the element. The standard capacitor symbol is useful for any type of capacitor, but if we're using an electrolytic capacitor, make sure to use the electrolytic specific symbol, and if needed, label the polarity of the device. Inductors also have a couple of common ways to represent them. You can use any of them, and if you have a variable inductor, again add a diagonal line, just like we did for a resistor. Generic diodes again look like this, probably fairly familiar. If you have an LED, make sure to add the little arrows representing light coming off of it. Schottky diodes will look like this far symbol, and Zener diodes will look like this middle one. When you're representing diodes in your schematics, make sure you use a symbol which represents the type of diode you'll actually be using. This will make your schematic much clearer for other engineers. Transistors again, there's a number of different symbols depending on the type of transistor we're going to use. If we use a MOSFET device, we use the MOSFET specific symbol. If we're using an IGBT or a BJT, we use the specific symbol for that type of device as well. Don't represent a MOSFET with a BJT symbol, it'll be confusing for anybody looking at your schematic. When dealing with op-amps, we need to keep in mind whether or not we want to represent the voltage rails on the device. If we do, we add this top and bottom line as seen in the first symbol, and if not, we use the second symbol. If there's any ambiguity about what the voltage rails are going to be, simply use the first symbol to avoid it. Various other integrated circuits are generally represented by a square or a box with some pins coming out. We'll go over those a little bit later. Ideal sources and sinks, we have our voltage source and our current source you're probably familiar with. Additionally, when representing schematics, we use ground symbols so that we don't have to connect all the ground nets. And we can use either of these two symbols, or sometimes even a triangular symbol like this. It doesn't really matter, just make sure you're consistent. So let's take a look at some example circuits people have drawn. All of these circuits are trying to implement an op-amp with a non-inverting gain of positive 2. So we'll just go through them one at a time and see what we like and don't like about all of them. This first schematic up here, you can see we've labeled one of the resistors, but the other one simply doesn't have a value. So that's pretty bad. We'd like to add a value to it. Additionally, we haven't labeled the voltage rails on our op-amp, which makes it a little bit confusing. Nowhere on this circuit does it say we're using 12 volts. So for those reasons, we don't like this first one. The second attempt is obviously misleading. You can see we haven't labeled input, we haven't labeled output. Additionally, if we follow the data flow, we're going from left to top, which is very weird and non-standard. None of our components have either designators or names or component values on them, so we don't like this. Additionally, we haven't labeled ground. There's a lot of problems with that. Try to avoid that completely. This third attempt over here is again very confusing. When you just look at the circuit immediately, it's not clear where the input and where the output are. Turns out this is the input and this is the output, but it's not readily clear just by glancing at it. We also don't have component values for our resistors, as well as the fact that if we follow the data flow, we're kind of going from the middle to the left. That's non-standard, very confusing. We don't like this at all. The fact that we used a battery for our voltage source is actually fine, because we may implement that as a battery. Jumping down to the lower left, we're getting closer, but still not where we want to be. When we draw circuits, it's standard to put the highest voltage rails on top and the lowest voltage rails on bottom. And you can see that we flipped that in this circuit. We have our 12 volts below our ground symbol. That's non-standard and we don't really like it. Other than that, this circuit's looking alright, but because of that, we're not going to use it either. Jumping over to lower right, here you can see we've used this rectangular symbol for resistors, and that's fine because we've been consistent with it. But we've managed to draw this circuit with an extra jumper there, so we've had to jump 2 wires over each other, which you actually don't have to do with this schematic. Additionally, when we labeled our capacitor, you can see we label it as 0.1 times 10 to the minus 6. You should have just written 0.1 microfarads. It would have been much clearer. So for those two relatively small reasons, we'll not use that either. The schematic that we really like is this middle one on the bottom. You can see we've labeled all of our components with designators or names. All of our components have values. We've labeled input and we've labeled output. You can see we use microfarads instead of 10 to the minus 6. Voltage rails are above ground rails. Data flow goes left to right. It looks really good. We like this one. Aim for something that looks like that when you're drawing circuits. Now all these same things we talked about will apply if we're representing our circuit in some sort of simulation program. This is a schematic taken from LT-Spice, and you can see again all of our components have designators as well as values. Data flow goes left to right. We've labeled things micro, not 10 to the minus 6. Even our op-amp has a part number and a name. Additionally, we have our voltage supply rails above our ground symbols. And because it's a simulation program, we were able to add a helpful text box to show us what this circuit should do. We like this. If you're implementing things in a simulation program, go for something that's clean and nicely laid out like this example. So there was a couple of common little rules that we just sort of went over when we were looking at those example circuits. So let's take a look at how those will apply to a larger circuit. Now, first of all, you notice we've labeled all components. They all have names or designators. Sometimes we use those terms interchangeably, as well as values, and that's true for every element here. When we labeled capacitors, you'll see we started each name with a C, so C2, 3, 4. Resistors start with an R. When we have an op-amp or a IC of some sort, we always start that name with U. Voltage sources start with a V. It's just common naming. We'd always use a V for voltage and I for current, stuff like that. Try and be consistent. It'll make things slightly easier. We showed parts and unit numbers, standard naming conventions, inputs and outputs labeled. You'll see we have our input is actually this voltage source over here, and we've nicely labeled that. Our output's labeled with this symbol. That's pretty nice. In addition, we've labeled some important signals inside of our circuit. So you can see trigger, discharge, CV are all labeled. That's going to make it easier when we're debugging to quickly find the important signals, or what we thought was important when we built the circuit. Unambiguous connections. It's kind of hard to get ambiguous connections in a simulation program, but really focus on that if you're hand drawing circuits. And then just in general, our data flow goes from left, here's our input, to right. And then we want to try and make that happen whenever possible. So left to right, as well as our voltages, high voltages on top and low voltages on bottom. So we have highest voltages top to lowest voltages bottom. That's sort of the standard we want to follow. Left to right in terms of data flow, top to bottom in terms of voltages. So that covers how to draw schematics, give you some tips as to best practices, how do you represent these components. Let's talk about reading component values for a little bit here, so we can, when we're transitioning from our schematic to an actual hardware piece, we'll know how to get the right one. So resistors, one of the most common elements we'll use. The things to note about these when you're selecting them. First of all, they all have a tolerance, so 1, 5, or 10% are the most common, and that means that when it says it's, for example, 220 ohms, it's actually plus or minus 5% or 10% based off of that. The other thing to pay attention to is the power rating of your resistor. Commonly these will come as quarter watt or maybe half watt components. Probably some of these first few are quarter watt. We have some half watt. You'll notice we even have a 4 watt resistor right here. You just make sure you get the I squared R or V squared over R, the equations for our power in a resistor. Make sure that you check you're not going to go above that, and even check that in your circuit you won't get close to that power rating. Resistors will get really hot and they can even burn up. Most of these, what we call coaxial resistors, where we have these two leads coming off the sides, we designate their value with a set of color bars. It's usually 4 color bars, sometimes 5. And let's just do an example of how we're going to read these. So, using this guy right here, first things first, if you have a gold bar or a silver bar, that's always the last color bar, so start reading from the other side. Here we have a gold bar, so we're going to start from the other side, and we have yellow, purple, green, gold. So yellow, purple, green, gold. Now, to read these, we reference a table, which the easiest way to get one of these is just Google resistor color codes. That'll pop up a number of different options, and we just start by reading it off. The first 2 color bars are just going to give us a number, and here we have yellow, so that's 4, and then purple or violet is 7, so we've got 47, and the third color bar gives us a multiplier. So let's see, the third color bar is green. Green is going to be a multiplier of 100K, so we're going to have 47 times 100K is going to be the nominal value of our resistor. And you could do a similar thing for any of these other ones. You notice for here we've got the gold bar on top, so we start reading from the bottom, so we'd have orange, black, blue, and you just reference the table to get that. Then finally there's going to be a tolerance here, so the last bar is gold, reference that in our table, that's plus or minus 5%. So really this resistor value could be any value within this range, plus minus 5% of 47 times 100K. So be aware that you might not get the actual value that you want. When you're grabbing resistors from a tub of resistors, there are some standard values that you can use, and these are the only ones that are going to be available to you in the circuits lab. So if you wanted to use, for example, a 30 ohm resistor, you'd either have to use a 33 or a 27 ohm. And these are all multiplied by 0.1, 1, 10, 100. So if you wanted a 500 ohm resistor, you could use 510 or 470 ohm. You're not going to get 500. So just be aware of that and pay attention to tolerances. That'll matter when you're building some timing circuits. Capacitors also use a standard convention for designating their value. Most of these, what we call film capacitors, or some of these smaller capacitors, will use a 2 or 3 digit code on the side in order to determine the value. If it's 2 digits, such as this small guy down here, then it assumes picofarads. So 22, and because there's only 2 digits, we just assume picofarads, so 22 picofarads, and that's the value. So some of these smaller resistors will do that. Some of these smaller capacitors will do that. If we have a value which isn't easily represented with picofarads, generally there'll be a 3-digit code on the side. For example, this capacitor down in the bottom is 103 labeled on the side. So we read the first 2 digits just as we would with a 2-digit code. So we have a 10, and then the third digit becomes just like the multiplier on a resistor. So it's going to be 10 times 10 to the third because we have a 3 there. So you just put whatever this third digit above the 10, and then we again assume picofarads. So we've got 10 times 10 to the third picofarads, which if you just write that out a little bit easier is 10 nanofarads. So that's how you read 2 and 3 digit codes. If you have one of these larger electrolytic caps, which you guys will use in the lab as well, much easier to read the value. It's pretty much always just written on the side. You see we have a 220 microfarad, 100 microfarad, and a 47 microfarad down here. Additionally, these electrolytics will generally label their voltage rating on the side, so 35 volts for that guy, 16 volts for that guy. That's the voltage that you don't want to exceed. Don't go above that voltage across the capacitor. Now remember, electrolytic capacitors are polarity sensitive, so they will have a negative terminal, and generally that's clearly labeled by some other color bar. So this will be the negative lead, and the negative lead would be on this side of that part. The other smaller capacitors, these film and ceramic capacitors, don't have a polarity, so they can be put in either way. Diodes are a little bit more complicated than our resistors and capacitors. Remember that current will flow only one way through this diode, so we need some way to designate the cathode of all these devices. And in packages like we see up here, which are the ones you'll be using in lab, there's almost always an extra color bar, so it's silver on these, there's a little black band on these, and that bar represents the bar on the diode symbol, so that's the cathode. Current will flow from the other side and come out of that bar. If we're using a light emitting diode, which generally look like this, they usually have a slightly flattened edge, which will be the cathode. Additionally, if the leads haven't been cut yet, one of the leads will be slightly shorter than the other. The longer lead is usually the positive terminal. You can also just carefully apply a small voltage to these with some current limit, and if it lights up, it's in the right way. You get the point. So, when we're looking at data sheets for these diodes to figure out how they operate, there's a few parameters they'll generally give us. The first one is the breakdown voltage, which is, if you remember your current voltage characteristics of a diode, that's the reverse voltage, which is actually going to cause the diode to stop blocking current. You're going to get this avalanche current. Sometimes this is destructive, and it might break your diode, so don't apply a reverse voltage larger than this breakdown voltage. Additionally, they'll generally give you a forward voltage drop, and that's at some test current. They'll just maybe apply 1 milliamp, and they'll say, well, the forward voltage drop there is 0.7 volts or 0.8 volts, something like that. They'll give you those two numbers. Just remember that that value is taken at a single test point. So, if we went up to 3 milliamps, the voltage would increase as expected. When you're using LEDs, they'll generally give you a nominal current. It's some number of milliamps that you'll get the correct brightness and the correct lifetime of the device if you operate at. So just find out what that current is and try and have your diode operate there. But those are the general characteristics they'll give you. Forward voltage drop, nominal forward current, and breakdown voltage for all of these devices. We'll take a look at an op-amp just as an example of the first IC we'll use. And remember, we've got two different ways of drawing these. Let's focus on this second way right now. Now, when you get this chip, the first thing you'll want to do is look up the part number online and find yourself a data sheet. Once you've found the data sheet, you can scroll a few pages down, and regardless of the chip, there will always be this pin-out diagram, as you can see here. And what that's going to do is relate the pins on the device inside to what's on the outside of the package. So for instance, if we just use this first op-amp we see here, output's pin 1, so that'll be pin 1, our negative input is pin 2, positive's pin 3, ground's pin 4, and VDD is pin 8. So just relate them like that. You'll see this package actually has two separate op-amps inside. It's important to note that they share a ground and a voltage rail. So if you apply power to one of them, the other one's going to have power as well. Now, physically, these will look something like one of these three chips up here. You'll notice that each of them has maybe a small dot on it, or a little divot on the side of the package. That'll let you know which is pin 1 for this device. And pin 1 will always be directly below or to the left of that. It orients this device for you. So we know that this is pin 1, so that's going to be the first output. And then just count down. Remember how they label them. You can see this chip labels it 1, 2, 3, 4, and then loops around to the other side, 5, 6, 7, 8. So 1, 2, 3, 4, you'd have 5, 6, 7, 8. Just take a look at the data sheet and follow exactly what it says. On the top of the data sheet, somewhere near the first couple pages, you'll end up with usually a bullet list, sometimes it's a short paragraph, which will give you a brief description of the capabilities of the chip that you're using. It's a good idea to just read through those and make sure everything sounds like something that you could use. You know, there's going to be some things you don't care about. For instance, we may not care about bias current, but the things we do care about, rail-to-rail output, make sure they're there and make sure that this chip will actually satisfy your needs. So that sums up this module. Really focus on these best practices. It makes it way easier for other people to help you debug, as well as for you to reference old designs and see what you've done. When we're drawing schematics, the big thing is try to avoid ambiguity. We want there to only be one way to interpret what you've drawn. If you can manage that, it's a pretty good schematic probably. And then really the big thing with building circuits, component tolerances. Know that your resistors and capacitors aren't going to have the exact value they state. There'll be some plus or minus. And when you get a new IC, always go read the data sheet. Go take a look, browse through it. There's a lot of useful information in there.